In this video, we'll talk about characterizing probability distributions using kernels. So we have seen how to represent each individual data point through an embedding in some feature space, and this allows to compare data points by evaluating the kernel between them, which acts as a measure of similarity between data points. But now we are interested in comparing two or more sets of data points, and more generally, distributions of points. And we'd like to be able to tell whether, as a distributions, these sets of points are more or less similar to each other. And we'll do this using kernel methods. And as a disclaimer, some of the figures and slides are borrowed from the lecture by Arthur Gretton, which you can find in the link below. So we'll start by some motivations. And the first one is the task of comparing two probability distributions. So we assume we are given some samples from unknown distributions P and Q. So for instance, we are given images of dogs that are drawn from the first distribution P, and then images of fish that are drawn from a distribution Q. And the goal would be to be able to tell just from these samples how P and Q are different, or if they are equal to each other. So the data could also have a different format. For instance, it could be a time series. So each sample would be a particular time series. And when you draw several samples from the same distribution P of time series, then you can still have a lot of variability. It can be hard to tell just from sight whether the samples actually look the same or not. And this is particularly the case when we are dealing with time series such as brain signals. For instance, here the local field potential. And one might be interested in measuring these local field potential under different conditions, experimental conditions. So one setting would be when there is a spike burst. A question would be to understand whether these spike bursts has an effect on the local field potential that we can measure. And to do that, we can have an experiment where we measure these field potentials under two different conditions, whether there is a spike burst or not, and we'd like to compare them. And what we observe is that the time series that we collect have a lot of variability, and it's really hard to tell from sight how these distributions are similar or different to each other just from sight. So one approach we could do is to take the average of these time series at each time step. We can compare and see whether there is a difference between the two distributions P and Q. But this can still be a not so satisfying answer because, well, first, there is a lot of variability. As you increase the number of samples, you might get a completely different average just because there is a lot of noise. And also, when you just simply average data, you might lose a lot of information, which be still relevant to discriminate between P and Q. So is there any more principled way to compare distributions that still retain some information about the data, and that is also easily adaptable no matter what the data format is, okay, whether it is an image or a time series. Another task would be, for instance, detecting dependence between samples. So let's say you are given a pairs of samples x1 and y1, and x1 would be a text, some text in English, and y1 would be its corresponding translation in French. So here, if we know that it's the corresponding translation, we expect there is a strong dependence between both samples. But in general, if you are just given these pairs and you're asked whether these are dependent or not, then you might want to devise a method that can tell you just by looking at the data whether this is the case or not. Well, in the previous example, we wanted to detect dependence between samples that are discrete, but you might also want to answer the same thing for samples that are continuous. And this very toy example, we are looking at pairs of samples x and y that are in this continuous space, two-dimensional space. And one approach you would like to use is to try to fit the density of the joint distribution P of xy And you will see that it has some shape here when we plot the isolines of it. And you want to compare it to the density that is formed by taking the marginal of each dimension, okay, the marginal of x and of y, and then multiplying them together, which correspond to the case of independence. That would be the case if x and y were independent, then the joint density would be just a product of the marginals. And so we can plot that, and you can see that it has a shape that is very different from the one of the marginals when you have a dependence. So you could compare the joint densities to the product of the marginal and say whether samples are dependent or not. But this strategy is unfortunately hard to generalize when you are dealing with high dimensional data, because you need to estimate the density beforehand. And instead, we would like a method that avoids this direct density estimation so that it's more scalable to high dimensional data and data sets that are of different formats. Okay, so to achieve this, we will introduce the concept of kernel mean embeddings, which is a way to represent a probability distribution in a feature space defined by a reproducing kernel hyperspace. And before doing so, we'll start by simple examples and then build some intuition about what these mean embeddings might look like. So in this example, we are just dealing with two Gaussians, which have the same variance, but different means. And we would like to be able to tell whether these Gaussians, how close they are to each other, or if they are exactly equal. So one idea would be just to look at the mean of the samples produced from each distribution. So we can compute the empirical mean for samples from P and those for Q, and you can compare the values of these means, and this gives you some information on whether the two Gaussians are actually equal or not. But now, if you have instead two Gaussians with the same mean but different variances, these are still different distributions, but if you just consider their empirical means, then there is no real efficient way to distinguish between those Gaussians because they simply have the same mean. So the idea would be to look at some higher order features, and in this case, it would be sufficient to look at the second moment. So if you look at jointly the first and second moments, you can compute an empirical estimate of those under samples from P and Q, and you end up with a two-dimensional vector where the first component is still this empirical mean, and the second one is the second moment, or the empirical estimate of the second moment, which captures some information about the variance of the distribution. And so now if you compare these vectors and treat them as a summary of your distributions, you might be able to tell if there is a difference between P and Q. But now, if you are given more diverse set of distributions that includes, for instance, a Laplace distribution, and you'd like to compare it to a Gaussian, if we take the scenario when both distributions have the same mean and variance, we still know that these are two different distributions because they have a very different densities. It will not be enough to just look at the first, second moments and compare them because they would be exactly equal by construction. So you might want to look at higher order moments or to introduce additional features that you'd like to compare. So in that case, you might want to form a vector of higher order moments of order 3 or 4 and so on. And you'd like to compute estimates or estimate the expectations of these moments under P and Q just by using the samples. So again, here, by introducing enough moments, you might be able to distinguish between P and Q. How can we define such features in a principled way so that we can always compare between distributions and confidently say whether they are equal or not? And this leads us to the concept of mean embedding that we formalize now. So given a kernel defined on a topological set with corresponding RKHS, a mean embedding of some probability distribution P defined on this set X is a function that associates to each point in X a number. And this function is actually an element in the RKHS that is defined as an expectation of the kernel under the distribution P. So the mean embedding is just the expected kernel value under P. The second variable is what defines the mean embedding as a function. We'll see that this notion of mean embedding has a lot of parallel with reproducing property that you've seen in previous lectures. So first, as you might recall, if you take any 2 points x and x prime, then the kernel between x and x prime can be expressed as a dot product between the kernel features in the Hilbert space. And there is also the kernel trick that tells you that any function in the RKHS can be reproduced in the sense that its value at any particular point x can be obtained by taking the dot product between f and the feature kernel k at point x. Now we can extend all these notions when talking about probability distributions. Well, first, given any two probability measures p and q, you can compute the expectation under p and q of the kernel just by taking the dot product in the Hilbert space, the RKHS, between the mean embeddings of P and of Q. And we also have access to a generalized kernel trick, which allows to compute the expectations under P of any function in the RKHS just by taking the dot product between F and the mean embedding of P. So this is a nice property of the mean embedding because it just allows to extend the kernel trick. So just to summarize, the kernel mean embedding is the one that is obtained by taking expectation of the feature kernel under a distribution P, and it generalizes the kernel trick. So you can think of it as a summary of the distribution P. And it allows to compute expectations under P for any function that belongs to the RKHS. And in practice, because it can be written as an expectation of the kernel, then you can estimate it using NIID samples just by taking an empirical average of the kernel. Visually, if you try to compare this to a density estimation, well, you might find out that for a specific choice of kernels, let's say a Gaussian kernel with a suitable size for the bandwidth, it would approximate actually the histogram of the samples. So the kernel mean embedding can be thought of maybe some representation that sometimes might look like the density or an approximation of the density. Of course, if you really want to approximate the histogram, you will need to adjust the bandwidth as you increase the sample size. But that's not the case here because the bandwidth will be fixed because you fix the kernel first, and then for any sample size, you compute the mean embedding. So at some point, even if you increase the sample size, the mean embedding will not converge to the density. So far, we introduced this notion of mean embedding, but we just assume that it exists and it satisfies this generalized kernel trick. But is that actually true? Is there really an element that belongs to the RKHS and that satisfies these properties? Well, actually, this will be the case, but under some additional assumption on the kernel. So this is shown in this proposition. So if you have a probability distribution, which is Borel on some set X, topological set, then if you choose a kernel that is positive definite and assume that it has an expectation under P that is finite. So more precisely, the expectation is of the square root of the kernel. So whenever this assumption holds, then there exists a unique element, mu P, that satisfies this generalized reproducing property. And in particular, it can be expressed as the expectation under P of the kernel, which recovers exactly the definition of a kernel mean embedding that we introduced. And the proof of this statement is actually very simple because it relies on Rie's representation theorem. For that, you can consider the linear form that acts on functions in the RKHS by taking their expectation under P. And under the assumption on the kernel, we can show that this form is actually continuous or bounded. And to do that, it's very easy. You can just use the definition of the linear form and the fact that we are applying it on functions in the RKHS. So the reproducing property holds so that we can upper bound the value or the absolute value of the linear form by this quantity, which involves a dot product between f and the kernel feature map. And then using Cauchy-Schwarz inequality, we get the last term on the right, which involves this expectation of the square root of the kernel, which is by assumption finite. And this shows exactly that the linear form is bounded, which then allows to apply Reed theorem, which then shows that there exists, guarantees that there exists an element in the RKHS such that the linear form can be written as a dot product between f and this element mu p, which is the mean embedding. And this concludes the proof. Now that we have introduced the kernel mean embedding, we are in position to use it in order to define a similarity measure between probability distributions. And this will be done through the concept of maximum mean discrepancy. So remember here, the goal is that we are given some samples from two distributions P and Q, and we would like to measure how P and Q differ just by looking at the samples. And to do that, we will consider one particular way to measure similarity between distributions, which is called the maximum mean discrepancy. And what this maximum mean discrepancy does is just looks at the RKHS norm of the difference between mean embeddings of P and Q. So this makes sense because we said that the mean embedding is a summary of a distribution. So we just compare the difference between two summaries of two distributions and measure their norm. And this should be a reasonable way to tell whether two distributions are close to each other or not. But what is interesting is that this quantity here that seems abstract actually has a nice expression just in terms of expectations of the kernel under probabilities P and Q. Okay, so the first two terms are expectations under P and Q of two independent copies, x and x prime, from the same distribution, either P or Q. And then the second last term is an expectation that involves both samples from P and Q. So the first two terms, we can call them intra-similarity terms because they measure the similarity of samples within the same distribution. And the last term can be called an inter-similarity term as it measures similarity between samples from two distributions that might be potentially different. And you know what the MMD does is that it computes each of these terms and compare how much, whether the inter-similarity between distribution P and Q is of the same order as the intra-similarity for each distribution P and Q. And if that's the case, then this would probably mean that P is actually equal to Q. But if the intra-similarity is of a different nature than the intra-similarity, then there might be some discrepancy between the distributions. But in general, the MMD is not a strict metric, meaning that if it is equal to 0, it does not necessarily imply that P is equal to Q. But for some particular choices of kernels, which we'll call characteristic kernels, the MMD is actually a metric, meaning that whenever it is 0, it guarantees that the two distributions are actually equal. Of course, the converse is always true. If P is equal to Q, then they have the same mean embedding, and then the MMD is 0. So from now on, we'll just assume that the MMD is a metric, meaning that we already made a good choice for the kernel so that it is a characteristic kernel, and then it retains all information about the distributions. But we'll say more about these characteristic kernels in a different video, and especially under what conditions we can say whether a kernel is characteristic or not. For now, we just assume that the MMD separates distributions. So now that we have defined this way of measuring similarity between probabilities, we might be interested in estimating it just using samples. And if you remember the expression of the MMD, which involves only expectations under the kernel, well, here we can replace these expectations by empirical averages. So given that we have samples from P and Q, we can arrange those samples to compute a similarity matrix on which the diagonal term would correspond to this intra-class similarity. so the similarity within samples of the same distribution, and the off-diagonal terms would correspond to the interclass similarity, that is similarity between dogs and fish, or samples between two distributions. So a natural estimator of the MMD would be just to reduce each block of this matrix and average them, and then consider the empirical version of the actual expression of the MMD. So in this case, we need to sum the diagonal terms and subtract the block diagonal one. But it turns out that this estimate of the MMD is biased. And the reason for the bias is that for the same index I, it will just compute the kernel between sample I and itself. And of course, the same sample is not independent from itself. This introduces a bias because, in fact, the expression of the MMD involves taking expectation between independent samples. To get rid of this bias, what one can do is just discard the diagonal terms, which then ensures that you're only computing the kernel between data points that are always independent. So this gives you an unbiased estimate of the MMD. And this is the one that we'll be using. Now that we have introduced the MMD and a way to estimate it using samples, which is very easy to compute as it only involves evaluating the kernel, it is worth retrieving the MMD using a different definition, which is the concept of integral probability metric. So this will provide a different insight on the MMD. Here we need to consider a set of measurable functions. So this would be a set of test functions that will define a quantity called integral probability metric, which will measure a discrepancy between two probability distributions in the following way. So basically, it will compute the expectations under two distributions P and Q of any function that belong to that set and take the supremum value of these difference in expectations. This defines some measure of how different P and Q are. And of course, if P was equal to Q, then this quantity will always be 0. And one can recover the MMD by choosing F to be the unit ball in the RKHS. And we'll see how this actual definition is exactly equivalent to the one that we provided in the beginning of the lecture. But it's worth noting that you might end up with a completely different divergence depending on the choice of the metric or the set of functions or test functions. So for instance, you can recover Dudley's metric by choosing F to be the set of bounded continuous functions. Recover the Kolmogorov metric by taking functions that have bounded variation, and the one-Wasserstein distance by taking functions that are bounded in Lipschitz. So these are distances that are harder to compute because the set of test functions is too big, in fact. So estimating them using a finite number of samples is quite challenging. You might get into trouble. This is not the case for the MMD because it simply has a closed form expression. So that's an advantage of the MMD, is that you can estimate it easily using samples. So one reason why this integral probability metric is useful in that it gives you an interpretation for the optimal function that achieves this supremum here. And we'll see that this function always exists. So this is a function that will assign positive values to these high density regions under P and negative values to high density regions under Q. And that way it completely distinguishes between the two distributions. Now let's see how we can recover the original definition of the MMD. We start from the definition, and then we use the fact that expectations under functions in the RKHS can be written as a dot product with their corresponding mean embedding. So here we can express the problem as that of finding a function in a unit ball that maximizes the correlation with the difference of mean embedding between P and Q. And of course, the function that maximizes the correlation would be just the one that is collinear with this vector. but that is constrained to be in the unit ball. And in the end, the optimal function would be the one that is exactly this difference in mean embedding that is normalized in terms of the RKHS norm. And this optimal function is called the witness function. So if we plug it in the expression of the MMD, we just recover exactly the RKHS norm of difference in mean embeddings. So the two definitions are really equivalent. Okay, so now we have introduced this notion of kernel mean embedding to compare probability distributions and the maximum mean discrepancy, which gives us this measure of similarity between distributions. And now we're going to talk about applications and how we can use the MMD for statistical testing and learning generative models. But we'll start with statistical testing. First, the general framework is that we are given some samples, IID samples, from two distributions, P and Q. So we call x1 to xn the samples from P, and y1 to yn the samples from Q. And the goal would be to be able to say whether P is equal to Q just by looking at the samples. Assuming that we have made a careful choice for the kernel, we can estimate the MMD between P and Q using these samples, and we consider the unbiased estimate of the MMD. And just to make the statistical framework a bit more precise, the scenario when P is equal to Q would be called the null hypothesis. And in that case, we would expect this empirical estimate of the MMD to be close to 0. And then the other scenario is when P is different from Q, and it's called the alternative hypothesis. And in that case, we should expect this estimator to be far away from 0. How close or far away should the MMD be from 0 in order to be confident in saying that P is equal to Q or not? And this is what we would like to make a bit more precise. So to do that, we'll start by looking at the fluctuations of the MMD, or the squared MMD, in both scenarios. So let's first start with the scenario where P is different from Q, which is the alternative hypothesis, because this is the easier one. So if we repeat the experiment, if we keep drawing many samples from P and Q that are independent and estimate the MMD at every time, we can draw a histogram of the squared MMD that is scaled by square root of n. And when we do that, we see that this histogram will start looking at like a Gaussian distribution. Okay, so that's the red curve plotted here. And that's actually is a known result, which says that the fluctuations of the MMD will be asymptotically normal. So as you scale the MMD squared by square root of n and subtract its expectation, which is the true MMD between P and Q, this should converge in distribution to a Gaussian that is centered in 0 and which has a variance that is some quantity that depends on P and Q, but which we'll not discuss here. But the important thing to remember is that the fluctuation will be Gaussian, and they would be centered around the actual mean, which is the MMD. And now let's look at the other scenario, which is when P is equal to Q. And now if we repeat the experiment many times and plot the histogram of the squared MMD, but with a different scaling here, we just multiply by the number of samples, then we see that this histogram would be actually not really like a Gaussian. It will be a bit skewed. First, it's not symmetric, and it has heavier tails for positive values, and it's a bit truncated for negative values. And also, you will notice that it puts a lot of mass around 0. This distribution can be actually exactly described. So this is a result that quantifies the fluctuations of the MMD under this scenario where P is equal to Q, and as you increase the sample size. So it says that the limiting distribution would be of the following form. So it's an infinite sum that is weighted by some coefficients lambda I, and we'll see these are non-negative coefficients. And it is multiplied by some random variable zi squared minus 1. So zi would be independent rows from a Gaussian. And what are these coefficients? Well, these would be the eigenvalues of some linear operator, which looks like the operator that you've seen in the course on Mercer kernels. So basically, it's an expectation under some measure. And here in particular, it would be the distribution P of functions that are convolved with a kernel K tilde. And this kernel K tilde would not be exactly the kernel that is used when estimating the MMD. It's a centered version of the kernel. Basically, this kernel would be the one that is obtained by subtracting the mean embedding from the features and taking the dot product. So this has the following form. And the linear operator that is defined here is symmetric positive and can be shown to be compact as well. So it has a discrete spectrum, and the eigenvalues will be non-negative. So this is the distribution that results in the case when P is equal to Q. So it's a highly non-trivial distribution, and it's actually not easy to estimate because you need to find the eigenvalues of this operator. But to summarize, when computing this estimator of the MMD, we will have two different behaviors for its fluctuations, either a sum of chi-square in the case where P is actually equal to Q, or a Gaussian when P is different from Q. And here the statistics of interest would be not the MMD on itself, but it will be scaled by the number of samples. So that in the null hypothesis, when the null hypothesis holds, then we converge to this sum of chi-squares. And when the alternative holds, we converge to some distribution that has a mean going to infinity because it is scaled by the number of samples, and also a variance that spreads linearly with the sample size. This Gaussian, which is the blue curve, centered around the point that goes to infinity as you increase the sample size, and it gets spread out as you increase the sample size as well. If your statistic that you compute falls in a region here, then it would be a low density region for the scenario when P is equal to Q. So you might say that it is very unlikely that P is equal to Q. But to be much more precise, what we'd like to do is to fix a significance level alpha, which is a positive number smaller than 1, and its corresponding quantile, which is a scalar C of alpha. And this quantile is defined so that the probability of the statistics that we observe in the scenario where the null hypothesis holds, meaning that P is equal to Q. So this probability that the statistics is greater than the quantile C alpha is equal to alpha. So this is how we define the quantile here. Typically, we choose alpha to be a very small number. And this probability corresponds to the case where we are under the null hypothesis, but we observe a very extreme value of the statistics T0. So in practice, what this means, if we really observe that T0 is greater than the quantile C alpha, we can reject the null hypothesis because it is very unlikely that this happens. And otherwise, if T0 is smaller than C alpha, we cannot reject the null hypothesis, meaning that P is likely equal to Q. Okay, so the thing is, if we had access directly to the quantile C alpha, then we might be able to perform the test easily. The problem is that the density, the red one, is very complicated, right? Because it involves some eigenvalues of some unknown operator. And so it's hard to compute the quantiles directly. What we're going to do instead is just try to do this a bit indirectly to decide whether T0 is greater than the quantile C alpha without actually computing directly this quantile. And for this, we'll assume that we can sample from this red distribution. And we'll see later how we can define a mechanism to be able to sample from this distribution, the red one. So for now, assume that we have a random variable that is according to the red density. And we'll be interested in computing the probability that this random variable is greater than the observed statistics T0 that we computed using the data. So this quantity would be called the p-value. And if the p-value is smaller than alpha, then this means directly that the statistics that we computed must be greater than the quantile C alpha. And this is just a result of the monotonicity of the quantiles. So because of that, all what we need to do, in fact, is just to estimate this p-value. We do not really need to estimate the quantile itself. We just need to estimate the p-value. And to estimate the p-value, well, we can try to sample from the red density multiple times. So J samples, for instance. Once we sample these random variables, we can estimate the p-value just by counting the number of times each sample is greater than the statistics T0. So whenever it is smaller than alpha, we can reject the null hypothesis. And so now remains the question of how do we construct these random variables? So this will be achieved using a permutation test that we'll see now. If you remember, the way that the MMD was estimated is first by producing or collecting a vector of samples from P that we call here X. So this would correspond to images of dogs. And then a second vector Y of samples from Q, which correspond to images of fish. And then you can compute the MMD by forming the similarity matrix and averaging each blocks and summing up all these blocks. So this is the expression that we get. But now what you'll do is, instead of taking the original data, you will shuffle the data randomly and form a new set of vectors, X tilde and Y tilde, which contains proportions of dogs and fish in such a way that in the end, these vectors or these samples have the same distribution, which is a mixture of P and Q. So in the scenario where P is actually equal to Q, we did not do anything because it's just mixing samples that are independent, and this doesn't change their distribution. But the thing is, we know for sure that X tilde and Y tilde have exactly the same distribution because they are just taking samples and shuffling them all around. And so we can estimate the MMD of these shuffled data, again, by forming a similarity matrix, which now does not have any particular structure, and you can estimate the MMD. So now the resulting estimate that we get is actually, we can claim that it's a sample from the red density that we are interested in, simply because these samples are really coming from the same density, which is the mixture of P and Q. And so we can repeat this experiment by every time shuffling the data in a different way randomly and computes the MMD statistics that is scaled by the number of samples. And so this allows to estimate the p-value and then to conclude whether one should reject or accept the null hypothesis. So this is a nice way that one can use kernels in order to perform statistical tests on arbitrary data just by choosing a suitable kernel and then applying the same procedure once this is done. So we've seen this application on statistical testing, but there's other applications that are of interest, and one of them would be to learn generative models. So here the scenario is that we are given some data which are sampled from a distribution P, and we would like to learn a model that can produce new samples so that these samples look like the ones from the data. There are several ways one could achieve this, and one general method that we can call explicit generative modeling is to define a model Q through some density defined on the data. And this density is parameterized by some vector of parameters that you would like to learn, for instance, using maximum likelihood on the data. So once you learn the model, you can produce samples using methods like Markov chain Monte Carlo. But there is an alternative way of modeling distributions, which we'll call implicit generative modeling. And in this case, we do not define a density on the data or on this data space directly, but what we do instead is to define a generative mechanism for samples. And in this case, what we'll consider is the following mechanism, which samples a latent variable z from some simple distribution like a Gaussian, and then it feeds this sample to some network or some function g that then will compute a sample from the model, which we'd like to be close to the data distribution. And this function here would be a parametric function, such as a deep neural network, that we would like to learn, and so that it produces samples that are close to P. What is interesting about this approach is that it works even if there is no density for the model. And that can happen if, for instance, the latent variables have a small dimension, which is smaller than the dimension of the output samples. And the training, in that case, since we do not have access to the density of the model, which might not even be defined, it is impossible to use the maximum likelihood in general. So instead, we would like to minimize some sort of divergence between the data and the model Q. And we'll see that we can use the MMD as such divergence. And what is interesting with these models is that sampling from them is very easy because you just need to sample a latent, which is easy to sample from, and then compute this transformation of the latent using the map that you would have learned. So this is by contrast to explicit modeling, which would require in general applying Markov chain Monte Carlo. We will focus on the second approach, which is implicit generative modeling, because this is the one for which the MMD, as you'll see, is very natural to use. One application of implicit generative modeling is single image super resolution, where you are given as input some image, and you'd like to produce a higher resolution image from it by filling up the details in the image. And the way it would work is by feeding this original image to a generator network that would take also some additional noise as input and will produce this higher resolution image as output. Another application is image-to-image translation, where, for instance, you'd be given a segmentation map that you would like to use as input and produce realistic scenario that corresponds to such segmentation. A second application is where you are given images from a satellite and you would like to transform them into a map where it's easier to recognize the streets, for instance. Finally, another application is where you are given a text which describes a potential image that you'd like to generate. And given this description, the model will be able to produce images that correspond to this description. But of course, the description is not totally exact. So there are a lot of details that are not defined. And the generator would fill in these details. So for instance, here, there is a description on a bird, the shape of the bird, the size, but there is no information about the pose of the bird. So the generator might be able to decide which pose the bird would be in. Okay, and so a general approach to learning these models, implicit generative models, would be to define a divergence between distributions, in this case, the data and the model. And this divergence is itself defined by maximizing some variational objective. And this objective depends on functions that belong to a set that is predefined. And this definition actually recovers integral probability metrics that we've seen in the previous slides. In a particular case, when this variational objective consists in the difference of expectations of the functions f under p and q. So here, these functions will act as a critic that's allowed to distinguish between p and q. So it finds the regions of differences between p and q. And once the best critic, the one that maximizes the differences between P and Q is recovered, then the generator is optimized so that it reduces the discrepancy between samples from it and the data. And in particular, one can recover the MMD when choosing F to be the unit ball in the RKHS, as we've seen earlier, and by choosing a specific form for the variational objective. So in this case, the problem becomes just to minimize the squared MMD under the parameters of the model. And there is a nice way one can do this, which is scalable and exploits the stochastic optimization framework. And in that case, what you can do is just sample at each iteration. You can sample a mini batch of data and then sample another batch of latent noise. And for each of these noise, you can compute a sample from the model just by feeding the noise to the generator network. And once you've done that, you are given two sets of samples from P and from Q. So we can use these samples to estimate the MMD between the data and the model. And this estimate actually is a function that is differentiable in the parameters of the model. And its gradient can be computed simply by using automatic differentiation. And so you can update the parameters of the model to minimize the MMD just by using this stochastic gradient. So if you do this, for instance, on MNIST dataset and using just a simple Gaussian kernel, you can still get a model that learns to generate decent digits, but you can also notice that there are a lot of artifacts, which are these dots in white, which should not be there. And this is in practice coming from the choice of the kernel, because here we just chose a Gaussian kernel. And so it's really hard to define a good measure of similarity using a Gaussian kernel on a high dimensional data set like an image. But it's also hard to design a specific kernel for complex data sets like images. So one approach would be to learn these kernels. So a variant would be to, instead of just fixing a kernel at the beginning and then try to optimize the MMD, instead one would consider a family of kernels, and among this family to figure out which kernel maximizes the distance between P and Q and the model. And this kernel would be selected because it is the one that would discriminate the best between P and Q. So once this kernel is found, then one can optimize the parameters of the model or of the generator just by minimizing this optimal MMD. And one can define such family of kernels in a very simple way, which is as follows. So basically, you would pick a fixed kernel, like a Gaussian kernel, that would be defined on some feature space. So instead of taking as input the row pixels directly, it would take some features of the data. So here, these features would be computed by some neural network. And the parameters of this neural network would be what defines the family of kernels. So these are all positive definite kernels by construction. And the goal would be to find the neural networks or the kernels that maximizes the MMD between the data and the current model. And when this is done, then you can learn the model or perform an update to the model. So then what this does is that it adaptively selects an MMD that best discriminates between P and Q. And in practice, to solve this problem, you need to alternate between gradient steps on the parameters of the kernel and gradient steps on the parameters of the model. So it recovers this adversarial training framework. So if you do this now, still using the same generator, but changing the kernel and learning the kernel adaptively, you can get much better samples, which get rid of these artifacts that we've seen in the previous example. So the samples, we can arguably say that they are better looking. And you can even apply this approach to much more complicated data sets like Celeb A, which is a data set of images. This was just a quick overview of generative modeling using the MMD, but there is more to the story. There is a question of regularization when learning the kernels, which is very important because it has implications on how well or how stable the optimization will be. There is a question of evaluation of the quality of samples. So when you are given samples like this in a high dimensional space, it is really hard to evaluate whether these samples are better than other slightly different samples produced by a different model. And there are ways you can do that with the MMD, of course, but it's still an open problem in general because the choice of the kernel would matter a lot. So to summarize, so far we've seen that it's possible to represent probability distributions using kernels through the concept of mean embeddings. And by measuring distances between mean embeddings in RKHS space, we can define a distance that allows to compare between probability distributions, which is called the maximum mean discrepancy. And this discrepancy is nice because it has a very easy way to be estimated using samples, and it can be used for various applications such as two-sample tests and for learning implicit generative models, which we discussed. But there are also other applications that we did not talk about, such as dependence detection, where we'd like to decide whether two variables are independent or not, and feature selection and blind source separation. So all these applications and the context that we considered so far assume that we have access to a good kernel, which does not discard information about distributions. And we call these kernel characteristic kernels. But we would like to make this more precise and especially to be able to tell whether a kernel is a good kernel or not, and more precisely whether it is characteristic or not. So this would be the object of the next lecture.